Welcome again, and in this video we'll quickly go through some properties of discrete time Fourier transform, and you will see that there's a lot of similarity as was with the analysis with respect to the properties also, but there's one property, and in fact we'll be starting with that property. That is a property of the periodicity. And discrete time Fourier transform is always periodic. In omega, that is, and the period is 2 pi. Okay, so which means in terms of an expression that x e j omega will always be equivalent to x e should I write it j omega plus 2 pi. Right, you can easily prove it, just make some substitution. So in a mathematical form, x e j omega is equivalent to summation n runs from minus infinity to plus infinity x of n e raised power minus j omega n, and x e j omega plus 2 pi will be equivalent to summation n from minus infinity to plus infinity x of n e raised power minus j omega plus 2 pi n. Then if you expand it, x of n e raised power minus j omega n into e raised power minus j 2 pi n. Now this term, it's always unity. You can use a Euler's relation, it will turn out to be unity. So we are left with this, n is equivalent to minus infinity plus infinity x of n e raised power minus j omega n, which is in fact x of e raised power j omega. Okay, so this is the property of periodicity for the discrete time Fourier transform. Then we have properties that we did in the continuous time case, like we have the property of linearity, according to which if you have x1, you have a sequence whose discrete time Fourier transform is, let's suppose, x1 e j omega. Then you have a second sequence x of 2n whose discrete time Fourier transform is x2 e j omega. Then if you make a linear combination of these two sequences, something like this, a x1n plus b x2n, then do their transform, it will be a x1 e raised power j omega plus b x2 e raised power j omega. Right, so this is the linearity property. Again, you can just make the substitution and you will come up with this. So I'm not going for the proof here. You can use the same analysis that we did in the continuous time case. Then we had the three basic properties. We had a property of time shifting. Again, quite similar to what we had in the continuous time case. You have x of n, you perform discrete time Fourier transform, you will get x e j omega. And if you shift your input by some amount, say n naught, it will reflect in the Fourier transform as an exponential factor. So this is quite similar to what we had in the continuous time case. Fine. Then there is folding, or what we can say the time reversal, which is something like this, x of n, you perform the discrete time Fourier transform, and what you get is x e j omega. Fine. And if you do time reversal, it will be reproduced in the Fourier transform. So something like this, you will have x of e minus j omega. exactly same जो आपका continuous time case में था, right? Then there is a property of what you call differencing. Again, sometimes we use it because again this is unique to discrete time case, because in continuous time case you have differential equations that are in terms of derivatives. Discrete time case में तो differential exist नहीं होगा, so we have difference equations. Instead of differential equations we have difference equations. So it is something like this. Again, if I have x of n and it transforms under the discrete time Fourier transform into x of e j omega, then if I define a difference expression, it is just that from the current sample you are subtracting a previous sample, right? Since subtraction is involved, difference operation is involved, we say this is a difference equation. तो इसका जो discrete time Fourier transform होगा, it will be 1 minus e raised power minus j omega x of e j omega. Fine. And you can easily prove it from the time shifting expression. Now, if x of n has a discrete time Fourier transform of x e j omega, then by time shifting, x of n minus 1 will have a discrete time Fourier transform of e raised power minus j omega. You can just use this expression, x of e j omega. So which means if you perform the difference x of n minus x of n minus 1, इसका जो discrete time Fourier transform होगा, it will be x of e j omega minus e raised power minus j omega x of e j omega, which in fact is this thing, right? Again, this is a property that is unique to the discrete time case, right? Because we don't have differential equations in the discrete time case, we have the difference equations. Then there is the property of scaling. Yeah, to be precise, scaling in time. Fine. Yeah, sometimes we call it time expansion. Right? Now, if you remember the continuous time case, if I scale my time, by time I mean the independent variable, and I perform the Fourier transform, it uses to scale my amplitude as well as the frequency. It was something like this, right? Which made sense, which kind of made sense in continuous time case, because if you go for the scaling operation in the continuous time case, it can either lead to the expansion of the signal or the compression of the signal, depending upon what the value of a is. So if a lies in the range 0 to 1, your signal will be expanded, and if a has a value greater than 1, it will be compressed, right? But discrete time case is slightly different. Again, if you go back to your first chapter, if you perform scaling, time scaling in discrete time case, and if a has a value which is greater than 1, you will lose samples. And if you remember from our first chapter, some of the samples will be lost in your output after you do the time scaling. And that is something we don't want, because if you are trying to analyze a signal, if you are trying to, here analysis means transferring from the time domain to the frequency domain. If you're trying to do this kind of operation, you will definitely want to have the signal in the time domain intact, right? So we can't, I mean, it doesn't make sense that you lose samples and then transform it to the frequency domain. So that's why we call it expansion. That is, we can have scaling wherein we try to expand the signal, in the sense that we try to conserve our samples. We don't want to lose our samples, then go to the frequency domain. So as far as this property is concerned, we have a slightly different way of expressing this property. Okay, so what we do is we define an integer k, Fine. Then define the scaling operation in terms of this k as x of n by k if n is multiple of k, and 0 if n is not a multiple of k. Okay, this is a slightly different way of representing what you call the scaling operation. As an example, in terms of a waveform, चलिए मैं directly बनाता हूँ. Suppose I have a signal x of n, it is defined for some points 0, 1. Similarly on the negative time axis. So 0, 1, 2, 3, 4, 5, 6. Right? Then we have some sample values. Say for example 0 पे ये value है, 1 पे it goes down to 2. Could be arbitrary values, something like this. Right? So this is x of n. Then if I define another signal, say my scaled like this, I'm defining this signal. Say k has a value of 3x 3n, right? Which means k has a value of 3. Right? Now see here, x 3n will be equivalent to x of, this by the way is n, it will be x n by 3. Now if I take the first point n corresponding to 0, so it means x of 0, which means इस नई signal में the sample that exists as 0, it will still exist. Right? Now for n is equivalent to 1, that is x3 1, it will be x of 1 by 3. But 1 is not a multiple of 3 because you have a condition x n by k if n is a multiple of k. अब हमारा यहाँ पे k 3 है and 1 is not a multiple of 3. So in that case it will be 0. So 1 पे आपका 0 आएगा. Similarly, if we go for x3 2, we will have x2 by 3. Again 2 is not a multiple of 3, so it will have a value of 0. Then we have x3 3 to be x3 by 3. 3 is a multiple of 3. 3 by 3 is x1. So जो आपका 1 का sample है वो आप यहाँ पे आएगा. Okay, so this is 0. 1 पे 0, 2 पे 0, 3 पे आपका 1 का sample जो है. इसी तरह if you continue like this, there will be 0 samples on 4 and 5. 6 पे आपका 2 वाला sample आएगा. Then there will be 2 more 0 samples. Then फिर आपके 9 पे आपका 3 वाला sample आएगा. Fine. So this is an alternate way of expressing the time scaling operation. What it does, it expands your signal. आपके जो samples है, they will not be lost if you express time scaling in this manner. मैंने आपको थोड़ा explain किया that why do we want, because if we lose our samples in the time domain, we can't have an exact frequency description in the Fourier domain, in the discrete time Fourier transform. Okay? So we kind of alternate our things. We express the time scaling operation using this expression, and that's why it's called time expansion, because we are spacing our what you call samples. Like in this case, for every sample and the next one, we will have 2 samples in between jinka value 0, and same will go for the negative axis. We will have 2 empty samples, then -1 will be mapped here, then again 2 empty samples, then -2 will be mapped here, and likewise. Okay? So this is a better way of expressing time scaling operation. Let's put this. Fine. So now if we want to find it, what will happen into it in the frequency domain, next to eg omega, it will be n runs from minus infinity to plus infinity x k n e raised power minus j omega n. Fine. Now, and x of kn is defined here, that it is equivalent to 0 except for the case where n is a multiple of k. So we can express it something like this, कि अगर आपका ऐसा केस है n is equivalent to r and k being integers, then only it has a value. Otherwise, अगर ऐसा नहीं है, it is not a multiple of k, then the value is 0. So with this, we can say that xk e raised power j omega, instead of n we will use r. Limits वही रहेंगे from minus infinity to plus infinity, and you will have x of k r k e raised power minus j omega r k. Fine. So you can make a substitution here directly. So it will be r runs from minus infinity to plus infinity, and this, when this is true, इस टाइम पे आपका जो सिग्नल का वैल्यू है, it is x of r. Again, you can go to this example. इस इंटरवल पे this is satisfied, n is equal to r k in intervals पे, and you will see that कि जो value in sample points पे है, it is actually equivalent to the r. Fine. R is 1, ये value यहाँ पे आ गया, ये value यहाँ पे, similarly this. So whenever this is true, when n is multiple of k, so indirectly it means you have n is equivalent to r k. So you can have these values. Right? So whenever this is true, तो जो sample value इस पे है, that is basically the value of x at this point r. Then exponential तो ऐसे ही रहेगा j k omega r, and this basically is the Fourier transform of the signal j k omega. Okay? So which means हमारा जो property है, it is something like this, that if x of n has a discrete time Fourier transform of x of e j omega, then if you define a time scaled version of this signal, but kaise, in this, the way we define it here, this is important, not the normal way x of at in this sense. तो इसका जो discrete time Fourier transform होगा, it will be x e j k omega. Fine. So this is the thing. Fine. So we did the periodicity property, which was again unique to the discrete time case. So in continuation with this, if x of e j omega, it is periodic with period 2 pi. So जो आपका ये है new signal, or you can say the frequency version of a time scale signal, this will also be periodic, लेकिन इसका जो period होगा, it will be 2 pi by k. ठीक है. So these were some properties. बाकी जो properties है, they are exactly the same that we had in the continuous time domain. Like we had this linearity, time shifting, exactly the same the way they were in continuous time case. But there are some properties that are different, and prominent among them is this scaling and also the differencing. बाकी convolution या जो भी properties हमने continuous time case में की थी, they are quite similar in this domain also. Like I said, in this course we are mainly interested in the continuous time case. So we'll stop our discussion about the discrete time, although we have done a fair bit of analysis in terms of discrete time Fourier series and discrete time Fourier transform. But as far as this course is concerned, this is more than enough. So this basically ends your third chapter that was related to the Fourier analysis. But we had left one important topic by the end of our second chapter, which was basically sampling. sampling and their associated uh, theorems associated with the sampling. It's very important, especially for electronics. Sampling has a lot of significance because this is the starting point when you start to convert your continuous time signals into the discrete time domain, into a discrete time signal. So in the coming videos we'll have a discussion, we'll have a in detail discussion about the sampling, and I will be using this. That's why I delayed the discussion on sampling unless and until we were done with the Fourier transform. So we'll be doing sampling in time domain. It is pretty straightforward, but we'll be seeing what will be the impact, yeah, how we define, yeah, how we analyze sampling in the frequency domain, and from there on, from the analysis in the frequency domain, we will come up with certain restrictions that are allowed, that we have to implement, yeah, that we have to keep in consideration while doing the sampling, and those restrictions basically then define the sampling theorem, right? So that will be important, and that we'll be discussing in the next video. As far as your third chapter is concerned, it ends here. Thanks.